We learned QPSK or quadrature phase shift keying modulation scheme, which is a digital modulation scheme. And our next topic today, actually, we will concentrate on the signal constellation. This one, as we already have an introduction of QPSK. Um, well, let me recall the some of the key points in our previous video. We said that for QPSK, we set M equals to 4, which is M array modulation scheme. It is M array digital modulation scheme. So it is actually M array digital modulation scheme. Digital modulation scheme. So we keep M equal to 4. We have already discussed the M array phase shift keying, and if we substitute M equal to 4 in our M array PSK equation, we get the QPSK. If you recall your expression of the signal, it is given by Si of t, which is which we can write as a cos of omega ct, a cos of omega ct plus theta I. This was a generalized expression, and we said that I is from 1 to capital M, right? 1 to capital M. When we substitute this M equals to 4, when we substitute this M equals to 4, then we have 4 unique signals. 4 unique signals, and these unique signals differ by their angles. They differ by their angles, theta I. We already discussed this, and we also said that we can rewrite our equation in the form of this as a linear combination of psi 1 of t and this is si2 psi 2 of t. We can rewrite our equation as a linear combination of these basis functions, psi 1 of t and psi 2 of t, and these scaling factors s sub I1 and s sub I2 are the scalars, and they represent the images of si of t over psi 1 and psi 2 respectively. Well, we still need to verify, because in my last video we just said that okay, we can we saw the 4 signal points, and we said that our signal points as the coordinates of our signal points si1 and si2 are given by like e over 2, and here we have e over 2 for the first one. For the first symbol, when our theta I is pi by 4, when our theta I is pi by 4, when our theta is pi by 4, we have these coordinates. We it still need verification, because we did not provide a proof in my previous video that the energy of the signal, this si1 is actually equal to plus e over 2. I did not give you this proof, right? We just say that okay, si1 is under root e. We just mentioned this, that this is equal to under root e and cos of theta I, and we did not prove that actually si is equal to this. So let's see. I'll provide this proof, and then we will move to the signal constellation. So let me provide a proof first. So for I would for the proof, let me recall our psi 1 of t. Our psi 1 of t is 2 over t cos of omega ct, right? And our psi 2 of t, the second orthonormal basis function, a second orthonormal basis function, let me write it, it doesn't look good. The second orthonormal basis function, that is minus under root 2 over t sine of omega ct. We learned that psi 1 and psi 2 are given by these sinusoids, and these are orthonormal basis functions. And we just saw that our signal Si of t is a linear combination, right? Si of t is given by a cos of omega ct plus theta I, right? This is our signal Si of t. Now let's find the energy to verify that actually the image will be under root e over 2. First of all, let's identify what's the energy of this signal. So if I find the energy, let me represent it by E. So the energy of the signal is E, which is the square of the signal, integral of the, which is integral of the square of the signal, because our signal exists from 0 to t, so our limits will be 0 to t. So we have to find the energy of the signal by evaluating this integral. And if you substitute your integral here, you can say that okay, the energy is equal to 0 to t, and this will be a square cos square omega ct plus theta I dt, right? This is just the square of this signal in the duration 0 to t, this limit 0 to t. So if we find out this integral, you can just put a square outside the integral, and you can use the identity, mathematical identity, which is 1 plus cos 2 omega ct whole divided by 2. Not square, 1 plus cos 2 theta, 1 plus cos 2 theta, 1 plus cos 2 omega ct over 2. So we need to integrate it, and if you integrate this one, we can see that this is actually equal to a this will be equal to a square two integrals, right? Two integrals of dt, and another one is 0 to t cos 2 omega ct over 2 dt. Now you have to integrate, you have to evaluate these two integrals. So if you find out this one from here, it is very easy to evaluate. You will find a square t over 2 is the result of this one, and this integral, you can see that it is the this one is actually the sinusoid over a period, so it would give you 0. So this integral will give you 0. So if you see the energy of your signal, is actually a square t over 2 for the ith signal. So it is for every signal, this is the same energy. So we have m equals 4. So all the 4 signals, because we have generalized, find it for the ith signal. So for all S1, S2, S3, S4, all the 4 signals, we will get the same expression for the energy. Now Now keep this in mind. We will use this equation of energy later on. Now we find the energy of the same signal. We find the energy of our signal from this expression. If you see, we said that okay, we can also write our signal as a linear combination SI1 psi1 of t plus S sub I2 and psi2 of t. These are here's SI1 and SI2. SI1 and SI2 are scalars. Now, if we find the energy from here, let me find the energy from here. Again, the same process. We have to integrate the square of the signal, right? Integrate the square of the signal. So our signal is SI1 psi1 of t plus SI2 psi2 of t. Right? We have to integrate the square. We have to integrate this square. Now, if we integrate this square, you can just substitute the trigonometric identity, which is SI1 square psi1 square t. It's just like a plus b whole square. So a square plus b square plus 2ab. So you can write this SI2 square psi2 square t plus 2 times, or let me write it here, plus 2 times 0 to t SI1 SI2 psi1 t 2 times a and b, right? Psi2 t, and this is dt. Now we have to find this integral, a square plus b square plus 2ab. This will give us the energy of our signal. This will give us the energy of our signal. We already have energy from other expression. So if you look at here, if you see here, now let me find out this integral. Find out this integral, and the energy is equal to, now if you see, SI1 square is a scalar, right? So we have SI1 square is a scalar. From the first term we have inside psi1 square t dt from 0 to t, and from the second term I would write SI2 square outside, right? SI2 square is outside, and I have integral 0 to t. I should not write this integral because this is already covered it. 2 times this dt, and here I should put a bracket, right? Because this bracket starts here and ends here. A square. These are the term a square plus b square plus 2 times ab. Now from the second one, from the second and SI1 square, and I can say okay, psi2 square t dt. This is the second one. The third one, if you can specifically, let me write the third one as well. Let me write the third one, and this will be 2 times SI1 SI2 integral 0 to t psi1 of t psi2 of t and dt, right? Specifically I'll write this one. So these are the 3 terms, and we need to find out this integral. Okay, now let me recall this identity. Our energy is equal to SI1 square. Now why I write from the first term, if you see over here, this integral from 0 to t, this one, this integral, this is the square of the orthonormal basis function. So we already said that this energy is this is actually the energy of psi 1. So the energy of psi 1 is unity, so we get 1 here, and I will just write 1. Similarly, we can write from the second term SI2 square, and again the energy of this integral, this is the energy of psi 2, which is 1, so I would write 1 here. And from the third term, now you can observe that psi 1 and psi 2 are orthogonal, so you will get 0 from the third term. So our energy, the expression for energy actually equals to SI1 square plus SI2 square. Now this is our expression for energy, SI1 square plus SI2 square. Now comparing this equation with our previous one, we said that this energy, if you go back to the previous equation, we said that the energy of our signal is actually A square T over 2, right? The energy is A square T over 2. Now if we equate these two, and also we said that for the first, now let me specifically talk about the first signal for which our theta I, if you observe, theta I for the first symbol is pi by 4. So S1, if I draw my S1, on this psi 1 and psi 2 axis, where an angle theta I, it is just this line. Now with a 45 degrees, right? Pi by 4, 45 degrees angle. So wherever you stop over here, right, you will have the vertical component and the horizontal component are equal, right? This vertical component and this is equal. So because the angle is pi by 4, so for this signal point, these two images, which is the image over y-axis, these two images are equal. Now if I say that, okay, this is my, because here what do we have? We have these coordinates SI1 and SI2, right? These are the coordinates of our signal. When these are equal, we can now from this expression we can substitute our energy is equal to SI1 square, energy is equal to SI1 square plus SI2 square, right? Which can be written equal to 2 times SI1 square, because SI1 square and SI2 squares are equal, so you can write it 2 times SI1 square or 2 times SI2 square. You can also write it is equal to 2 times SI2 square. So both are equal. When you get this equation, this equality, okay, from this equality, now what you can do? You can verify. You can now it's already we got a proof. You can say that, okay, this implies that 2 times SI1 square is equal to E, right? And it implies that SI1 is actually equal to under root E over 2. This is how we prove that the SI1, which is this side, this image, this is actually equal to under root E over 2. So this is actually equal to under root E over 2. As SI1 and SI2 are equal, because we have the angle pi by 4, so this is also under root E over 2. If you don't take EI1 and EI2 equal, you still can prove this, that the energy, the total energy will still remain the same. But in digital communication, it is always taken equal. These are taken equal. SI1 and SI2 are taken equal because they are the images of the signal over the basis function. Actually, these are the coefficients SI1 for FC, for the carrier frequency. So carrier frequency, whether it is cos of omega 2 pi fct or whether it is sine of 2 pi fct, we have the same coefficients for both the carriers. Now this is the proof that okay, our SI1 is equal to this, and this is same as SI2 for symbol number 1. You can prove it for any other symbol. Just take that particular pi and verify that these actually equals to under root E over 2. Now what is signal constellation? With the signal constellation actually is just a representation of these signal points in Euclidean space. This is our signal constellation. So if you go to the if I write my signal constellation, if you go to your table 3.1 in my previous video and your slides, you can see that all the signal points S1, S2, S3 and S4, these can be plotted on the these psi1 and psi2, psi1 and psi2 axis, right? All these points can be plotted here, as we have just seen that our first point is here, signal point, which is S1. Similarly for S2 it is this one, and S3 the signal point is here, and S4 the signal point is in the fourth quadrant. So for QPSK signaling scheme, we have these 4 points, and this is known as the signal constellation. The signal constellation, the 4 signals, and their representation in the signal space diagram. Now as I mentioned earlier, that our data is in the form of ones and zeros. It is always in the form of one. So whenever you get data from a binary source, it would be something like this: 1 0 1 1. It will be some sequence of ones and zeros, right? It would be some sequence of ones and zeros. So when you want, what is the purpose of the communication system? To transmit. The communication system has to transmit this data successfully from transmitter to the receiver. So if we have a transmitter, and a receiver, distance receiver, we would like to transmit this data from transmitter to the receiver successfully. Now in BPSK we just transmit one bit per symbol. You can transmit, keep this in mind, you can transmit n bits per symbol, right? Log 2 of m. This is an identity. So in BPSK we have m equals to 2. So just 2 unique symbols, 2 unique signals. They differ by theta I, which is 180 degree, and we use one signal for transmission of 1 and another signal for transmission of 0. In QPSK we have M4. We have 4 signals. M is equal to 4. Now we have 4 unique symbols, S1, S2, S3 and S4. So we can transmit 2 bits because we have 4 different signals. So identification, we can group our data in group of 2 and we can transmit it these using our this constellation. The signal to be transmitted will be based on the binary sequence which you get from the binary source. So a signal to be transmitted will be according to the binary sequence. When we group the data into ones and zeros, we call a die-bit, and each die-bit. Now, what's the procedure? We will see it with the help of MATLAB as well. The procedure for the procedure is that the first one, you have two bits in a die bit, first bit and the second bit. The first bit will be transmitted by the cos carrier, cos of 2 pi fct, and the second bit will be transmitted by the sine carrier. So actually, if you see your signal, suppose we specifically concentrate on this one. We specifically concentrate on a transmission of 1 0. So for 1 0. Now another important I could just I have to recall that the bit assignment for these symbols is just like this: 1 0 0 1, and then you have 0 0 and 1 0. So whenever you encounter, the first 2 bits are 1 0. The first 2 bits are 1 0 from the source. So for 1 0 we have to transmit S4. We have to transmit S4. Now when you transmit S4, you actually transmit these two coordinates, minus E over 2, minus E over 2, and the first one, these are the coordinates of this symbol S4 in the signal constellation. We can read it, we can see it from the signal constellation diagram. So this coefficient will be transmitted over psi 1, which is cos of 2 pi fct, and the other one, this one, will be transmitted over psi 2, which is sine of 2 pi fct. We just add these two signals. First of all, we have to multiply a cos wave with this amplitude, which will scale that cos wave. Then we will multiply a sine wave with this amplitude, which will scale up that sine wave, and we add those two signals and transmit S4. We would add those two signals and transmit S4, which is actually given, which is discussed earlier, that when you want to transmit S4, of t, this is actually the scaled version of now I have specifically, I can write S4, right? I can write S4 1. This is my S4 1 psi 1 of t. This is the scaling of the cosine waveform. Similarly, the scaling S4 2 psi 2 of t. This is the scaling of the sine, the scaling of the sinusoid. And then there is an addition in between. So we have to add these two. This will make this symbol a modulated QPSK modulated signal. We call QPSK modulated signal, and this signal would be transmitted. This signal would be transmitted over this channel. The signal would be transmitted over this channel from here, from source to destination. S4 will be transmitted to successfully transmit this data. Successfully transmit 1 0. This is how the transmission would take place. So signal constellation is important for these, and we can see that in our signal constellation we can observe that all these 4 signal points, we can observe that all these four signal points, this one and this one, they have they lie far apart, and they are they have the same energy, because this is, now we can compute that this is from these coordinates you can see that this is the energy of this length is actually the energy of the signal, because each side is E over 2. If you find this side is under root E over 2, under root E over 2. So each side is under root E over 2. So when you can find both these sides under root E over 2, so we say that okay, this is under root E over 2, this is also under root E over 2, so the length is under root E, which is the energy of the signal. And this is from the signal constellation. And another important property of this constellation can be observed here, that all the four signals carry 2 bits. So all the four signals carry 2 bits, but see, the S1 carry 2 bits, which is S1, this 1 1, S2 carry 2 bits, 0 1, S3 carry 2 bits, and S4 carry 2 bits. And now each symbol, like S1, these are called the adjacent symbols. These S1. So for S1, S2 and S4 are the adjacent symbols. Similarly for S3, S4 and S2 are the adjacent symbols. So these are the adjacent symbols. We can see in this bit assignment that the adjacent symbols differ by 1 bit only. Adjacent symbols differ by 1 bit only. If you see S1, so S1, the first bit is 1, the second bit is 1. For S2, the first bit is 0, the second bit is 1. So the second bit is same in S1 and S2. So they differ by 1 bit. Similarly, S2 and S3, the first bit is 0. For S2, the first bit is 0 and the second bit is 1. For S3, the first bit is 0, the second bit is also 0. So you can see that the difference is this bit. The second bit, they have first bit same. Similarly, S3 and S4 have the second bit of S3 and S4 is same. So these adjacent symbols differ by 1 bit. This is called gray coding. This type of bit assignment is called gray coding, and we will see later on that the gray coding is important for reducing the bit error rate at the receiving side, because whenever you transmit your data from transmitter to the receiver, there is always possibility of error, because when you transmit your data from transmitter to the receiver, there is always probability of errors. You transmit from source to destination, so there is always probability of error. So if this symbol S1 can be incorrectly if it is detected correctly, you receive 1 0 correctly. If it is not detected, it will be either detected as S2 or as S4. In that case, if it is incorrectly detected and the adjacent, more probably it looks like the adjacent symbol. So if S1 is misdetect, it would be detected either S2 or either S4. So so that would occur a symbol error. That would cause a symbol error. So a symbol error occurs, and we can see that symbol error, if the symbol is incorrectly detected, it's still we have 1 bit error. So although the symbol carries 2 bits, but both the bits are not in error, because each adjacent symbol differ by 1 bit. So this is the importance of this gray coding, that when you have a gray coded assignment of bits to the symbols, or gray coded mapping, you actually get the for each symbol error you have just for one symbol error you have 1 bit error, 2 symbols error, 2 bits error. So actually 2 symbols carry 4 bits in QPSK, but if 2 symbols are in error, we would not get 4 bits in error, we would get just 2 bits in error. So this is due to this gray coding. So that's all about the signal constellation and the QPSK.